It is my great pleasure to welcome back to Cambridge François Dupressoir, who is now a lecturer at the University of Surrey, who is going to tell us all about verifying constant time implementations. François.
Hi. So yeah, thanks for the introduction. I'm not sure I'll tell you all about it, but I'll tell you what I know about it and what we can do as a team with these people to verify constant time implementations. So this will be presented, I think, next month at USENIX. So if you're there, go there and talk to Mike, who will be giving the talk, Michael Emmi. So what is this about, and why do we need to verify constant time? So before I go into constant time itself, I'll go first into Sidechannel Security in general and what it means. So the goal that we have, the overall goal, is to defend a program against an adversary, who can listen in on computation. So your computation is going on, and it involves some secret data, and you've got an adversary who is not supposed to know the code to the lock, but essentially you're giving it by some side channel, like a piece of paper next to the lock. And that side channel can be execution time, other timing channels like cache timing, so the adversary shares the cache with you and can, through the timing he gets from memory accesses, infer things you did on the cache state. Power consumption, so how much power your computation consumes, will leak information about the data you're manipulating. Micro-probing, where the adversary gets a probe very close to your processor. Electromagnetic emissions, sound, vibrations, everything essentially leaks information up to a certain extent and with a certain amount of noise added to it. And so we're trying to defend simple programs, in particular cryptographic programs, against that kind of attacks. And our assumption here, in this particular setting, is that the input-output functionality of your program is actually black box secure. So you've already got a proof of security for the input-output relation of your program. What you want to make sure of is that when you implemented it, you did not introduce any additional vulnerabilities through side channels. And having this black box security objective, which is what you want to achieve, actually informs the tagging of input as public or private, and the tagging of outputs as public or private. Public outputs and public inputs are going to be things that the adversary is given anyway in the black box security definition. And having this information, especially about outputs, which of the outputs are public, allows us to allow some leakage as long as it doesn't leak more than what the outputs actually leak, more than what the public outputs leak. So I'll give a bit more details about this. So this is broadly what Sidechannel Security is about, and our particular brand of Sidechannel Security, which is informed by the security property you want. And I'll be focusing mostly on Sidechannel Security against timing attacks. Timing attacks are attacks essentially based on the adversary measuring timing information, so execution time, fine grain or coarse grain. Those can be mounted remotely, or even cache timing attacks that can be mounted cross VM, for example, on a cloud server where resources are shared. And they have been shown to break black box secure crypto systems in the real world. So you have Vodney's attack on IPsec and TLS back in 2002, Lucky 13, Lucky Microseconds. All of those are attacks on the record layer of TLS up to 1.2 that were really successful and could just recover whole plain texts. On primitives like PKCS1, which is RSA encryption, you've got attacks like Blackenbacher and Mangers that were just based on measuring the time it took to undo padding, for example, and that would leak, also break the security of the encryption algorithm. And then you've got attacks on modular exponentiation that are cache-based in this setting, but you've got also simpler attacks that are usually well mitigated. And so you've got Percival's initial attack on modular exponentiation back in 2005, and more recently the cache bleed attack that was mounted despite countermeasures designed to avoid Percival's attack. And those countermeasures...
Where is that published? Cache bleed?
Cache bleed, I'm not sure it's been published yet, but it's been made public, definitely.
We missed it.
It was around the USENIX deadline that they made it public. So essentially,
Against which implementation did they showcase?
I think that was, let me check. I think it was GNU TLS, but it's in a lot of various libraries. So essentially, when Percival came up with his attack, the countermeasure that was added in most modular exponentiation libraries was not to make the whole memory trace constant, but make it constant up to cache block size. So you were hiding where in the cache line you were hitting, but you were not hiding which cache line you were hitting in. And so the problem is that's valid on some architectures, but not on some others. And so the countermeasures falls apart when you actually compile it on another machine.
Okay, so it is architecture specific.
This one is architecture specific, but it's because the countermeasure that was put in was designed for a specific architecture.
So it's probably an ARM attack, I guess.
So it's only against Intel Sandy Bridge.
It's against Sandy Bridge.
Yeah, and so countermeasures, there are two main schools. So one of them is balancing or hiding the leakage, where you allow some leak to happen or allow some secret-dependent timing variations in your secret computations, but then you try to hide them after the fact. So that's what's used in S2N, I think some other crypto libraries. The problem with that is that you've got an unclear leakage model and an unclear security model. What is it you're trying to achieve? How much are you trying to hide? And what kind of adversary you're protecting against? And then most of these countermeasures are based on adding random noise. And essentially, if you don't add enough, you can average it out. And if you add too much, then you probably end up hurting your application because you need to wait for 30 seconds whenever something fails, which is not usually a good thing. The other brand of countermeasures is ConstantTime Programming, where constant time is really, really a bad name for this. The idea is not to compute the upper bound of execution time and then make everything take that time. It's to make the timing, in some sense, with air quotes around timing. I'm not sure if there's a video or not. There is, cool. The timing independent of the secrets. So it can still depend on public inputs, but it should not depend at all on public outputs. And the usual way of modeling that is to consider the most leak-prone instructions. So branching, which is going to leak a lot because you're branching and doing two different things, so the timing of those two things are going to be different. But also memory accesses because of cache timing attacks. And other leaks that are much smaller and much easier hidden using noise are not considered. And then if an adversary manages to start exploiting them, then you would try to hide those as well and make them secret independent. The problem with this is that with this brand of countermeasure is that it completely breaks the code you're looking at, right? And it doesn't break it in the sense that it makes it non-functional. But when you're now trying to maintain it or read it and figure out what it does, it's just unreadable. Another issue is that because you're doing this at source level, the compiler can break your countermeasure completely through optimizations and put you back in it eventually and make you vulnerable again. So the idea now is to try and look at constant-time programming, which has a very clear leakage model, which is essentially you've got this set of operation that you want to make, whose leakage you have a model for and that you want to make independent from secrets, and you've got a language that you can work on. So let me give you a bit of a primer on constant-time programming. So I'll give a couple of variants of this code where you have a public interface that takes an unsigned length parameter, which is the public parameter in here. And you've got a public address out buffer, public address in buffer, and a secret offset in the input buffer. And you're going to copy something whatever is in the input buffer starting at that secret offset into the output buffer starting at 0. And you're copying the length bits or bytes that the adversary requested. And so one naive implementation would be this copy function here that loops over the entire buffer size. There's a more naive implementation that I didn't even put in. And then you're saying, if I'm within the range I should be copying, then I'm copying. If not, I just keep looping. And I'm actually leaving the loop as soon as I'm done copying what I wanted to copy. So obviously, this, through timing, is going to leak a lot of information. And in particular, you're going to go exactly through offset plus length operations, length being public and known to the adversary, and offset being the secret you're trying to hide. So that's definitely not good. If the adversary can, from looking at the source code and knowing the architecture, know how much an iteration takes, then you can get the offset value, your secret offset. So another variation of this would be to just keep looping until the end of the buffer. Do not break as soon as you've copied out, but only do this byte copy or assignment whenever you are within the range you're trying to copy. So here, you've actually got two possible sources of timing issues. The first one is that this statement here, the actual assignment, is going to be executed on the offset plus length time, so exactly the same as previously. But the timing difference between whether or not you're executing this statement is going to be smaller than what we had before. More importantly, however, the instruction cache is going to reveal if you're going into the if or the else branch. So the first time you're going into the then branch, you're going to have a cache miss, probably going to have a cache miss on the instruction cache. And then possibly when you go back into the else branch, you'll have another cache miss in the instruction cache. And so that cache miss is going to have quite a big leak, cause quite a big timing leak. Probably actually much bigger than whatever timing leak would come from actually executing an assignment or not. So we fix it again. And now we're going to say we're going to prevent branching on secret-dependent data completely. So that means we need to somehow make everything branch-free. And one way of doing this is to use masks. Well, that is the way of doing it. So you, instead of branching and saying if A is less than B, you're creating a mask that's going to be all ones if A is less than B, and all zeros if A is greater than or equal to B. And then you're going to be doing both branches all the time. I need to go down. Both branches of the computation all the time. So here you're doing this assignment all the time, but sometimes you're going to OR 0 onto the value, and sometimes you're going to OR the actual n of I, depending on the value of your mask. And so if I is less than the offset, if I is greater than or equal to the offset and I is less than offset plus length is now encoded into this mask, and then you do both operations all the time. But in this case, you still have some leakage that comes from the data cache this time. So here, the value of j is actually going to be incremented only when you're within the range. And so your trace of memory accesses that does leak into the shared cache, some piece of state that you're sharing with the adversary, that value of j is secret dependent over time. And so you're going to be leaking information about your secrets that way. And then there's a small possible leak here as well, where on most architectures, integer division takes a time that depends on the bit size of its operands. And here the mask is either all ones or all zeros, so the bit sizes are wildly different. And that might actually leak information about whether you're in range or out of range as well. And so finally, constant time implementation, where you're ensuring constant path, so no branching on secrets, and constant access, which is no memory accesses at addresses that depend on secret. And then we're also adding constant op in there, which is constant, whenever you have an operation that would be, whose timing would be input dependent as well, you can also try to put that into your model. Although here we don't really do it. And in this case, you could get this implementation that uses a constant time equality check, and that just now loops over the whole buffer and over the whole length every single time. So now you're in n square. Now the issue is, when you're looking at this code, you have no idea what it's doing. There's no way you can maintain this. If there's a bug in it, you won't find it. So it's bad. And if it's not constant time, there's probably no way you can figure it out looking at it either. And this is just a buffer copy, right? So actually, this kind of code is a piece of code that was recently, so this is a piece of code, not exactly this, but that was in OpenSSL as a countermeasure against Lucky 13. And one of the many copies of it in the OpenSSL source code was actually found to be vulnerable, not vulnerable to a side channel attack, but actually not functionally correct back in May, I think, or April. And it was just a fact of not checking that you're not reading past the end of the buffer. That was really, really bad. And now you've also turned your nice buffer copy that was linear in the length of what you wanted to copy into a big O of n square. That's not even an n square. It's buffer size times the length you're trying to copy. The buffer size could actually be very large. So that already is not normal in the sense that you're losing quite a bit in performance. So you're then trying to squeeze more performance out. And doing that, you're trying to get everything you can get out of each architecture, and that led to cache bleed. So you're saying, on that particular architecture, I know that the leakage looks like this, so I'm going to, squeeze that extra cycle out, and on another architecture is going to fall apart. So our objective, given all of that, is to verify constant time automatically. By automatically, we mean with minimal annotations, and then the rest is done by a tool automatically. We want a fine-grained, flexible leakage policy that could actually allow us to look at details of target microarchitectures. So if you are looking at a microarchitecture where the address within a cache line, the offset within a cache line is not leaked, then you could actually model it in our tool. And then if you're going to go for another microarchitecture that does leak that offset, then you can have a full memory trace leaked to the adversary. And we also want to allow some leakage if it's benign with respect to the target security property. So, I mean, this constant time copy is nice and good to have, but then if what you're copying out is an offset, so the offset that you're considering secret is actually then, in some cases, given to the adversary, then you might not want to use this one. You might want to do a linear copy. And we want to allow this. So if it's at this point secret because you haven't checked everything yet, but it becomes public eventually, it's a good thing to be able to optimize that n square away. Yeah.
So, I mean, one of the examples you've been showing so far have been C code.
Yes.
What of the compiler is going to do with C code?
So I show C code because it's readable and people understand it. So our tool works on LLVM code. Actually, this thing, maybe not this exact version of it, but in OpenSSL, these things are functions and not macros because GCC was optimizing them back into if then else statements.
But I think it's a general pattern that any compiler optimization, either for the LLVM or the C compiler, is supposed to preserve the input, the black box functionality,
yes.
right? But doesn't have any clue about the...
So I mean, we know compilers do bad things to constant time countermeasures, and that's why we're coming in after optimization. So I did not say this in here. Well, I say it just right next. So we want to verify low-level optimized code. Yeah.
GCC optimization, because when you do that optimization, is then lowered to a conditional move, and because of the way the superscalar architecture is laid out, that has less pressure on the register rename engine, so that has less of a timing attack than the clever one that's intended to
Okay.
constant time.
Okay, that's interesting to know. So actually, that's especially interesting to know if we're verifying directly that low-level code. That C move is actually less leaky than other possible.
Are you going to tell us more about benign leakage?
Sorry?
Are you going to tell us more about...
A bit more, but I actually realize now that I didn't put any interesting examples in there. But so one more interesting example than a final copy would be if you have encrypt and MAC, then when you do the decryption, so you do verify then decrypt, that the fact that the verification succeeded or failed is going to depend on the MAC key, which is a secret. So you want to be able to branch on that.
So my concern is that at least in principle, there are some attacks that would be adaptive attacks, where it's okay to release the information at the end, but not in the middle of the algorithm, and I'm wondering whether you are safe for those, or whether it requires some special care.
So because of the fact that our notion of public is something that is eventually given to the adversary, even if what you're releasing it in the middle, it has to be something that leaks out to the adversary.
But if the
that is
adversary
given.
can inject inputs that takes advantage of what was written in the middle, then it's not true anymore.
So you have a scenario where you have multiple oracles.
So you take one of those protocols that release the authentication key at the end, for example.
Yes.
And if you release the authentication key in the middle, then the adversary can inject the message, then obviously it's not going to be correct.
So you're not releasing the authentication key, you're releasing whether or not the check succeeded. That's what I mean by something that's eventually given to the adversary. And we're looking at individual oracle queries, right? So you're looking at the decrypt and verify oracle, or code.
So your notion of input and output is really for one block.
Yeah. So for one oracle, essentially what we're considering as public input is everything the adversary controls through the security experiment, through the security game, and public outputs are whatever information about the actual, not oracle, but actual algorithm's outputs is given back to the adversary by the oracle. So you have this oracle wrapper in your security experiment, and we consider that as for public and private. But I mean, that's a separate thing. Right here, you could just consider public annotations are given by the user. They're trusted. You tell me this is public input, this is public outputs, and we're fine with that. We're just taking that as an input to the tool. But yeah, we didn't actually consider things where you have experiments that could be in several stages. That would be an interesting lead for future stuff.
When you say program, what kind of program are you providing specifically?
So I'll tell a bit more about this, but we're looking at LLVM, optimized LLVM programs in this setting.
So the intermediate program from LLVM?
The thing that's just before linking.
I see. That's great, because actually, does that mean that I will be able to use your verifier to verify constant time implementation in higher level programming languages than C?
If you can compile them to LLVM, yeah.
Sure.
I mean, there is quite a bit of. So I'll go to the architecture. I think it's towards the end of my talk, but I'll describe what's going on. And there's quite a lot of information that's actually given to us by LLVM, so that we can do our verification. And some of it comes from the fact that it's compiled from C. So if you can give us more information than what the C compiler can give us, then we're very happy. If your compilation chain gives us less information, we might have to do more work at LLVM level, which is obviously more difficult. But it's a trade-off you have to come up with.
So in case if your tool says it's not constant time, what do? You have to change the high-level code?
Yeah, so if our tool says this is not constant time, first of all, you need to decipher what the error message means, which is always fun. So it's actually not so bad in most cases. But you still need to then trace it back to the point in the C program where that occurs, and then figure out if it's actually spurious or an actual
So this may be harder if you have a higher level language.
It all depends on how how much tooling you have, but yes. It might be harder, but it's on the tool developer to do it.
Presumably also less likely to have enough information to do the analysis if you've got something like Smoke where the IR is letting the calls out to the runtime library that have no timing guarantees at all.
So this is also a different issue, which is how do you model where do you stop verifying and how do you model leakage? So if you're really looking at an actual architecture, there's no information about which instructions leak what. You have no idea what the pipeline is doing, and so you don't have all the information you need to do this properly and precisely and soundly. So either you over-approximate and lose performance, or you say, I assume this leakage is small enough that it's going to be eaten by something else anyway. But it's always a trade-off you need to make between protecting against known attacks, which you assume are the best that can be done at the moment, and protecting against all attacks, which is always a bit more difficult and probably impossible. But yeah. So the general architecture we're going for is you get a constant time verifier that takes in annotations, a small amount of them, a program. So here we're taking C but compiling it down to LLVM. So we're annotating C just to make it readable and easy to deal with. And a leakage model, optionally. And that produces either, yes, this is constant time, or no, this is not constant time, and here is a possible trace that illustrates it. No, this is not constant time is actually, I can't prove that this is constant time. It's not complete. So the first thing we need to do before actually verifying constant time is actually specify it. So the way we specify strict constant time, where you don't have publicly observable outputs, is using non-interference. So this is just a very standard way of expressing that there is no information flow from public inputs, to a set of secret outputs. So this is the model. You have a program P, and you partition its inputs and outputs into public and secret subsets. And then you say P is non-interfering if any pair of executions that agree on the public part of their inputs also agree on the public part of their outputs. So this is P is non-interfering. And then how you can exploit this to verify constant time is that you mark public inputs as public inputs. And again, this marking of public is something that we trust in this particular setting, but that would be informed by whatever security property you want to prove. You instrument the semantics of the program to produce leakage traces. So whenever something is meant to leak in the leakage model you have, you just give it to the adversary. And then you mark the leakage trace as the only public output. And then if you prove that your program is non-interfering with respect to that setting, then you have strict constant time. There is no information flow from secret inputs to the leakage trace. If you want to allow publicly observable outputs, so public outputs, it's a bit difficult because public outputs would have to be proved to be equal. But here we want publicly observable outputs where we can assume that they're equal to prove that the secret outputs are, that the public outputs are equal. And so you now partition inputs into public and secret, and outputs into public, publicly observable, and secret. And what you want to prove is that any two executions of P that agree on public inputs and on publicly observable outputs produce, agree also on their public outputs. So here the publicly observable outputs are what is given to the adversary anyway in the black box model. So they could disagree because, for example, the MAC check would succeed with the correct key but fail with the wrong key. And you want to leak that information to the adversary. What you do not want to leak is if they do agree, if the MAC check fails in both cases, you don't want to leak whether the padding check failed in one setting and not the other. That's going into Python encrypt, yes. So that kind of padding oracles that you could get in Emmi would be captured by this. And so same thing, as I was just saying, you just mark public inputs and the outputs that are released to the adversary in the black box model as public in the, mark public inputs as public, mark outputs that are released to the black box adversary as publicly observable. I'll fix my slides before passing them on. And instrument the semantics to produce leakage traces in the same way as we did before. Mark the leakage trace as the only public output, so this time the blue kind of output. And run the verification tool, and voila, you get a verification tool that gives you security in this model where you allow some leakage that would be delimited by the information the adversary is given in the black box model.
So you're checking for non-interference on the leakage traces?
Yes. Still on the leakage traces, but this time with the additional condition that the publicly observable outputs need to be the same as well. So we're essentially pruning all the pairs of traces that do not agree on publicly observable outputs.
So do you do something special for random programs?
We haven't looked really at random programs so far. Essentially what we would do then is sample outside, make the randomness public, a public input, if it's actually given to the adversary.
In the most ideal case, you would have the exact same leakage trace every time with all inputs.
Yes, so essentially, in this case, so if you want pure constant without any dependency even on public inputs, that would be pure constant thing where everything, all inputs are marked secret, and then your leakage trace is marked as public output. And you can look at that, and in fact, many examples are like that. Right? Sorry, Cedric, what were you asking just a minute ago? I think I wanted to say something more, but I've forgotten what you.
Yes, it was random.
Yeah, random thing. So essentially, what one other thing you could do is actually possibly more less thought out answer is that you could prove that the distribution on the leakage trace is the same. So lift the equality to the distribution, and then you're good. But that might be more difficult to reason about. And definitely the tool that we have wouldn't do that, although the approach might apply quite well to it. The tool that we have wouldn't support it out of the box. It would require a bit more thought and engineering.
If you depend on the randomness for being constant time, then yes, that will require more work.
Yes. And actually, I invite you to look at the masking papers, because there you do depend on the randomness, not to be constant time, but to be secure against probing attacks. So in this picture, in these two pictures, there are two components, so marking public inputs and marking public outputs, and instrumenting the semantics to produce leakage traces. And so I'll go through both of these before actually saying how we verify that thing. So we have a simple annotation language that we currently have on C source code, just because that's convenient to have. And it actually makes it more usable as a tool for programmers as well, although it makes error reporting a bit more difficult, as Markov pointed out. And what we have in this annotation language is that we ask the user to mark public elements, public inputs, and public outputs as public, rather than asking them to mark secrets as secret. That means that if you run the tool without any annotations, it's going to fail by default and tell you this is not secure, and then it's your job to think about what you're going to give it as annotations. So for example, an example of annotations, you've got this decryption function, a buffer that's used for input and output. So initially it contains the ciphertext. At the end it contains the plaintext, and that returns the length of the plaintext and possibly 0 if decryption failed. The length of the input buffer and buffer that contains the key that would be fixed size, for example. And here you mark the address of the buffer and the length as public inputs, and also the contents of the initial contents of the buffer. There, the ciphertext is provided by the adversary, so it's also public. You also mark the address of the key as public. So here, public in value key, that's really the pointer value that's public and not the contents of that pointer, of the memory region pointed to. And then we would also mark the result of the decryption as public. So the length of the plaintext, for example, that's in a setting where length of the plaintext would be public, and whether or not decryption succeeded.
And the address of the decrypt function itself is implicitly public?
Yes, whenever there's a function call, we will be making sure that it's the same function. And so when they're direct function calls, that's guaranteed. When they're through function pointers, we actually do verify that they're pointing to the same location in memory in both executions. Sorry?
How do you annotate when you have a function pointer?
We don't annotate anything. The semantics do that. So essentially, the LLVM code that's generated does jumps and does the dispatching, and that's when we put assertions that the two addresses that are called jump to are the same.
Let's say you have a decryption function that maybe has a public argument, or a public argument has some unpadding function.
Mm-hmm.
How can you specify?
So in this annotation language, we would not.
You would not.
Yeah, so this annotation language, it's really prototypical. There are many things we can't do. And in particular, in one of the examples we're looking at, there would be something more that we could have done if we had a better annotation language. Then if you go in directly at LLVM and add annotations, then you can do what you want. But it's really a matter of convenience that we went for this. So this is for a small language for marking public inputs and publicly observable outputs. And then when we produce leakage traces, we just really instrument the semantics. So where you have, so here we would capture constant path, constant access, for example. If you have a jump, so to a function pointer, then you're saying what leaks about this state is the address you're jumping to. If you have a conditional jump, then you'd be leaking the condition and the address you're jumping to. And then if you have memory accesses, so here I just put load because of lack of space. Sorry, I don't know what's going on. Then you're leaking the address that you're loading from. Or if you have a store, you would be leaking the address you're storing to. And then if you want to extend this, you can also just add, if you have a division, you're leaking the bit size of the denominator.
What about
denominators?
things? Like if you have a divisions by zeros, this can also leak some...
So there is one thing I did not say. We assume safety. We assume memory safety and safety in the sense of...
Okay. So there cannot be any page fault or any division by zero, right?
Yes. So this is a simple here leakage model. We assume safety of the program and we assume its correctness. That's part of this is black box secure. If you have buffer overflows, it's unlikely to be black box secure anyway.
Well, you never know. You haven't looked at the OpenSSL code.
Is it black box secure though? So this is a simple example, but then you could essentially extend the approach to any leakage model where the leakage produced by each instruction depends only on the current state. So if you have, if you want to say, I don't know, something stupid, floating point operations are never safe, then you could actually say floating point operations leak the whole thing, the whole state. And we need control flow at the very least to be leaked. So this one, this leakage function here, these two actually on branching operations, are the minimal set of leakage that you need to have for our approach to be sound and complete.
The first assumption.
So I'll talk about this a bit. So essentially, I think, but again, this is a claim I'm making a bit without justification. If you have a state machine that encodes the leakage, this would also apply. But this is, again, without evidence and without much thought.
so on so instruction leakage depends on instructions that were executed before and after.
Yes. Yeah, so I mean, in a real processor, you'll have a pipeline that's going to put you in it. You'll have the cache state, which we're not modeling here, but I mean, we're over-approximating it by saying the whole memory, the exact memory address is leaking. But if you want something more precise, you might actually want to model full cache state in there. And there are plenty of other things like branch prediction units and all sorts of things that come in and could actually, make this either imprecise or unsound. But this is, you're given a model, and within that model, we're saying there's no leakage. And then everything else that the adversary could get, he needs to get by fighting for it. So, but we could extend, I think, to any leakage model that leaks at least the control flow and can be expressed as a state machine, finite state machine.
I'm confused with the unconditional branch, so you assume that it leaks.
Leaks your address you're jumping to because of the instruction cache.
But you assume that if you just go to the next instruction, you may still leak something, or you ignore that? Or?
That's going to be enforced by the constant path anyway. Constant path, by having these two, we actually guarantee that the program counter is preserved. Is the same in both executions as well.
Okay. Yes.
Right. If you have jumps that are safe and then all the other ones are +1, then you should be okay.
Yes. Okay. Thanks.
So leakage traces we model like this. We associate to every instruction. We associate one function that produces the leakage from the current state, and that's what we're working with right now. And then that's how we specify things, and now we try to actually verify those security properties. And so we are given a choice of many methods to verify non-interference. So there are type systems for this. However, they lack flexibility. There was a certified type system, sorry. I'm not getting shot by Andy, at least. So the type systems that have been proposed so far lack flexibility. That is a much better statement. And in particular, there was one a verified type system on ComCert x86, or a bit above, back at CCS 2014, I think, that we used in a previous paper, and that was just completely unusable. It made unrealistic assumptions about the code it was working on. Taint analysis techniques, so taint propagation and things like this, do not scale well because they're not really modular. They require the whole code to be present and looked at in one go. However, there are characterizations of two-safety, and in particular, non-interference as safety properties by transforming the programs in such a way that if you can verify safety of that transformed program, then you get non-interference of the original program. So I'll be talking about two of them before going into ours. So this is the solution we're going for. We're trying to find a transformation X that uses the annotations, the program, and the leakage model to transform the program in such a way that the program is secure if and only if that transformed program is assertion safe. So here, when I talk about safety from now on, it's not memory safety, it's not the program as a semantics, it's really the assertions that we insert in it succeed. So historically, the first such transformation to have been proposed was self-composition. So you take your program with its annotations. The leakage model I'm using here is the one I showed above, but the only thing that leaks here is a branching operation. So you take your annotated program, and you make 2 copies of it into disjoint memory spaces. So you prime all your variables, make sure that you don't have clashes and stuff like this. You make 2 copies of your program. You assume initially that your public inputs are public, so they're the same on both sides. At the end, you assume that your publicly observable outputs are the same, and then eventually you assert that your public outputs, so here the leakage trace, which is the leakage of branching, are the same. So here your leakage trace is just the parity of the secret and parity of secret prime, and you're asserting that they're equal. So that's one transformation, and it's been shown back in the early 80s to be sound and complete. So if that transform program is safe, if and only if P is asecure with respect to the leakage model L, so asecure being whatever security property is implied by these annotations. So here that would be, if you have two executions of this program that agree on X initially and agree on Y at the end, then leakage traces are the same.
It was really in the early 80s.
I think so. Self-composition was early 80s. So it's sound and complete. That's great. That means now all the burden is on Boogie and you guys. We don't have to do any more work. However, it's really hard on the safety verifier, so we're really not fair if we actually use that. It's really hard on the safety verifier because all relations between intermediate variables are completely lost, right? So here, you would have to infer back that Y and Y prime are the same, and things like this. Modularity becomes really difficult because you need to do that on each function or inline everything and then do that. Loops are really difficult because if you desynchronize them, then you're dead. And the number of paths, and all of that is essentially making the number of paths in the product program or in the self-composition exponential in the number of initial paths in P. So if you have a path-based verification tool, you're dead again. You lose scalability, you lose everything. So if we did that, that would really not be fair, and then we would say, yeah, those guys need to improve, but that wouldn't be what we actually want to say. What we want to say is we want to be clever about it and actually give you something that you can work with. So another solution is to use product programs that are essentially self-composition but made more compact. So here you assume that the control flow is the same in both settings. And that's where our assumption that the control flow leaks comes in. And that's why constant time and that kind of verification techniques works really well. So here you've got the same program. I'm dropping the publicly observable output for now. And you'll be seeing why in a minute. So you have the same program, different annotations. And the program you're producing on the other side, the transform program, is you first assert that the leakage at that point is going to be the same. And then you only have one copy of this if statement where each branch contains both branches, well, the branch of each of the programs. So you branch only once, and it's fine because you know that the branching that's going to be done, it's the same in both executions of the program. But you're executing both programs in each of the branches. So essentially, instead of having two copies of your programs like this, you're interleaving the two programs like that, I guess, and synchronizing control flow. So that makes loops easier to deal with, control flow easier to deal with, and now the size of your transform program is the same as your initial program as well. So as long as you have no publicly observable outputs, yes?
So the proof technique is similar to Simona and Portier's flow camel proof technique by type system, right? So where they assume that the programs execute in lockstep fashion, and then at the branch, they assume that at the branching points they're at the same types, and the outputs differ only in sequence. Mm-hmm. And at the join points, they assume again that the immediate.
Yeah. So I mean, this thing is not new. All of what I've been saying so far, starting from the point of saying what we want is reducing to safety, those are things that were known. Self-composition in the early 80s, product programs in mid-80s, I think. It's not much later. And definitely they've been used before.
Yeah, I'm just wondering the relation between...
It's probably very similar to lots of things that are done in information flow verification in other places. In particular, if you're verifying information flow and you're preventing implicit flows in the sense that you're preventing branching on high values, product programs are what you want to go for. So if you don't have any publicly observable outputs, then this technique is sound complete as well. which is why it's very good for that kind of things. If you have publicly observable outputs, you can make it sound incomplete as long as you annotate things. So you need a bit more annotations and a bit more work as well. Loop invariants, so if you have loops, they're synchronized because that's the assumption you make. And essentially, that makes loop invariants very simple to infer. So in fact, what you need to do is make sure that the loops remain synchronized throughout, and whatever leakage the loop body has is public, can be made public. And so what you have is you can do a taint analysis on the loop body locally on it instead of having to do it globally on the whole program. But what we actually do is a merge coarser heuristic that says all the variables that are modified by the loop body and are live at the beginning and at the end of the loop should be equal in both executions. And that actually works for all of our examples but one, where we need to go in and do a bit more work. So most of the ConstantTime programs that we've looked at are actually very, very easy to look at, even though they have loops. And yeah, as I was saying, product programs are really well suited to strict constant paths, so the one that has no publicly observable outputs. And also to those that have publicly observable outputs, as long as the control flow doesn't diverge between the executions. So if everything that diverges is the memory access trace, then you should be fine. So now we're trying to put in publicly observable outputs where the control flow diverges on product programs. And the problem is, if you try to assert it here, to assert that the leakage at that point is the same at the point where it occurs, that will fail because you don't know yet the value of y and y prime, and you don't know that they're equal yet. So that's a bit problematic because we want this program to be secure because the parity of the secret is essentially the final value of y, which is leaked. Or not the final value of y, but the difference between the final value of y and the initial value of x. So this is bad. We lose completeness here. If you do it the other way and say, I want to assert it down here, like I was doing in the self-composition setting, where you assert everything at the end, then the value of y here you're using, or of y prime, is going to be the wrong one because you took a branch here that was the wrong one for one of the two programs. So if secret and secret prime have different parity, you're not going to go into the same branch for both. And so here we lose probably soundness and completeness both if we do this. So that's bad. We need something more. And so the idea here is to actually combine product programs with self-compositions. So whenever you could diverge on the control flow, you say, I'm fine with this. I'm going to record that I might diverge, and I'm going to verify later that it's fine and that it doesn't leak more information than the public output does. And then do self-composition inside to gain back soundness and completeness. And this requires a bit more annotation in the sense that you need to mark, I'm fine with this bit of control flow leaking back to the adversary. So don't necessarily look at this trying to understand it. The paper is probably much more informative than this bad example.
What is L? Sorry.
L is just the leakage trace. So now you have an additional variable L that you're using to collect the leakage. So here you could see it as a leakage trace, but here we're using it as a stack of all the assertions you would be collecting. And so that allows you to collect all the assertions you would like to essentially assert at that point, and then assert them at the end after having assumed that the publicly observable outputs are the same.
So it's just a gigantic conjunction.
It's just a gigantic conjunction. And that's a cheap way of doing lists of assertions. I'm running out of time. Yes?
I mean, you spent a lot of time explaining that self-composition doesn't scale and it's not practical for our tools, but if you think at examples where you would have to introduce these kind of things, I would guess, for instance, as you said, Mac and non-crypt.
Yes.
This would happen at the outer level after you've done the thing, which means that you would actually have to self-compose a large chunk of the program, right?
Possibly. So the examples we've looked at so far were on the more trivial side, where the final copy would be the thing that we allow to branch. I did look at encrypt and Mac, and that worked all right. It didn't lose too much. But again, this is.
Would it have also worked?
If you have something much bigger, I have no idea.
Or if you had only relied on self-composition for the whole program, would it have also worked?
That's a good question. Yes. Thanks. So the way we implement it, I'll go very quickly through this. It's a whole stack of tools that are connected by makefiles, so it's a bit complicated. We take annotations and program in C to begin with, compile them with clang to LLVM, optimize that all the way down to the final LLVM output before linking, and then we feed that to Smack, which is a tool by Mike Emmi and Zvonimir, I forgot his name, and others. And that turns optimized LLVM assembly into Boogie code, and that's a one-to-one mapping that preserves the shape of the code and is very, very close semantically. So that doesn't, the assumption here is that transformation doesn't change timing, but really the code is, you could do a reading of it in parallel and be fine with it. And then we transform this Boogie code using the product program transformation. Currently, the leakage model is fixed, but that's just a matter of adding an input and input language and tool. That produces the product program in Boogie, and we just run that through Boogie and get the answer we want. So this whole stack of tools is why going back from constant time violation back to this input program is a bit difficult, but it can be done. I mean,
when you write product here, it's either product or self-composition, depending on whether you have some.
It's that selective product where you're doing product most of the time, and then if you have something that's released, you do self-composition underneath it. So why do we do it on LLVM? I think that's a question that was asked already, but I'll go over it again. So it gives us a bit of generality in the sense that we can do generic reasoning over many architectures in the sense that it gives us a proof on many compiled programs, but it doesn't give us a proof in the precise leakage model that would correspond to that microarchitecture. But that's already a first step, right? If you're not secure at that level, you're not going to be secure down here anyway. It's convenience. There are tools for LLVM that might not exist for x86 or x64 or ARM assembly, in particular Smack and related tools, but also LLVM analysis. So we rely a lot on the shape analysis that LLVM does and on a lot of loop detection and things like this that Smack does that would be a lot more difficult to actually re-implement on lower level assembly. And we still have already at LLVM level that gives us sound control flow and cache timing modeling. The gap between LLVM and machine code is actually very small, even though it has some differences. The main ones that could trouble us is register allocation, but that is fine with respect to control flow and cache timing. And then instruction selection, and that is not fine because you could select an instruction that leaks a lot. And this is getting us to the imprecise arithmetic leakage and things like this.
The instruction selection is N to M. So you get N LLVM instructions within a basic block, and you get M machine code instructions N. But if the thing that you're depending on from LLVM IR is the loop analysis, you actually have that also in the machine code layers. So how difficult would it be to apply the same techniques there?
It would not, actually. The main issue is really engineering the tools. And the main interest of doing it below is really to have more precise modeling of what the leakage is, which is something that chip manufacturers are not really happy to give up. But if you're happy with profiling the leakage yourself or assuming something about the leakage, then doing it at or you actually want a proof at x64 level, then you want to do it below. And I don't think it's much more difficult scientifically. It's going to be an engineering challenge for sure.
So the obvious difficulty that I can see for doing it with a real microarchitecture model is your instructions are now no longer independent. So we had one example where if you add a not in the middle of a loop, the loop gets twice as fast on x86 because it kills a false dependency of something in the registry naming.
Yeah, so that's definitely a case where we would want, I'm going to pass over implementation details, where we would want to have more information about what the processor actually does. And that would be useful not only for us to verify security, but there are lots of other application domains where being able to predict the timing of instructions in your, well, the execution time of your program is going to be useful. I was chatting with someone from Absent recently, and in the worst case execution time analysis that they do, they're really imprecise because they don't have information about what the pipeline does, for example.
So when your execution time depends on, for a typical x86 processor, the 60 instructions that are currently in the pipeline, would your approach scale to that kind of?
I'm not sure. This is something we need to look at. So one of the things I would really want to look at is, for some reason I didn't put it on this slide. I did, maybe. I can't see it. Is you have if you have a model for your leakage that would be a state machine, then you can instrument your semantics in the same way we do with instruction by instruction leakage annotations. But you have an extra dimensions to explore, which is the initial state of your state machine. So if you can somehow do whole program analysis and know in advance the initial state, then you should be fine. If you can't do that, then you explode.
You would have a state machine with a few billion states.
Yes.
People have looked at bigger. I'm not sure if that's going to be doable in combination with what we're doing already, but we could also do a first step, which would be refining that state machine into something that's only relevant to timing, for example, or to time leakage, or to security relevant time leakage. I'm not sure if it remains as big or if it gets smaller, if that's a big reduction or if it's a minor reduction. I really don't know. So other things we would like to look at, and this is what I was talking about, we rely on a lot of information that's coming to us from LLVM and from the fact that it's compiled from C and that a lot of information is preserved by LLVM. So if you want to look directly at low-level code that was written by hand, you might actually need to re-implement all those analyses yourself. And in particular, one thing that's getting us stuck on some examples is that you need to be able to properly separate memory regions that contain public data from memory regions that contain secret dependent data. And if you have a C program, for example, that does weird things like sets 0 on a whole structure and essentially collapses it all into one region doing so, then you essentially get stuck and have to get arithmetic invariance to clearly separate those two regions, which is something, if you're doing down directly at LLVM level, you're not going to get. However, if you're compiling from a source program or a programming language where you have this strong property or can guarantee and preserve those invariants through compilation, then you could use that to inform the constant time verification as well. Same thing if you have already existing annotations that you're using to verify correctness or safety. Those could be used as well to refine whatever analysis we're doing. So yeah, looking at complex leakage models like state machines, data-dependent models that we didn't really look at. So we kind of experimented with integer division, but the problem there is, again, if you are saying we're leaking the bit size of the denominator, then you actually need arithmetic invariance on your loops to make sure that you can actually prove something about the bit size. And so then again, having these annotations would be useful. The people from Escort that are presenting a paper at USENIX as well do proofs on floating point operations. And essentially, they're replacing all floating point operations with constant time variance, except those where they can prove none of the arguments are subnormal and would cause weird timing anomalies. But that proof is, again, something that requires strong invariance on loops. And and things like this. It would be interesting to look at whether or not we can make the invariant inference a bit more precise than our course. Yep, this looks like what we need. Let's plonk it in there. And then improve modularity. So right now we're just inlining everything and running the product construction on the whole program, which is not a problem because we only have small things to look at. But then if you do have self-composition bits that are quite big, then you might want to actually get modularity in the sense that that way, if you do have a call to decryption inside your branch to a decryption algorithm, then you might actually just be able to verify that is secure by product program and then doing the self-composition with that call in the middle. So that's something we would be interested in looking at as well. So that's all I have. I went way over time, so thank you a lot for all your questions and your attention. Thanks.